talking about safe nonlinear control, particularly through a lens of machine learning and robustness. So I'm going to start by motivating this talk with a statement that sounds controversial but isn't too far from the consensus in this field, which is that machine learning is not ready for safety critical control. And what I mean by that is that there is a role for learning currently in the perception stacks and the behavior prediction stacks. But if you look at an autonomous car almost anywhere on the road today and you look at what's controlling the brake, the steering, the acceleration, it's going to be a model-based controller and not something that's just the output of a neural network. And this work is trying to focus on how can we build a theoretical and a practical understanding of how we can close that gap. So I want to start by talking about what does safety look like in the context of control. So given some dynamical system where we have the derivative given as a function of state, input, and some disturbance, we have messiness in the real world that we want to account for, and some feedback controller, we're going to say that a system is safe if it avoids any unsafe regions and it reaches some goal despite the impact of this uncertainty. So if you're taking a flight from Boston to New York, you want to make sure that you avoid all collisions and you land on the tarmac. So that's what we're going to mean when we talk about safety. If we look at the body of work on machine learning for control that's out there, there are a couple of columns that I'll fill in here gradually. But I want to start with something that most of you have probably heard of, which is reinforcement learning. This has, in the last 5 to 10 years, had a surge in popularity, largely due to its great performance on a range of challenging control problems. It's very easy to use. There are a lot of standard baselines out there for reinforcement learning for continuous control tasks. And although there's this high upfront computational cost in training these controllers, when it comes to running them online, they can be very fast. However, there are a couple of gaps when it comes to reinforcement learning in safety-critical contexts. One of the biggest gaps is transparency. When you have an end-to-end trained control system, you essentially have a black box neural network. You hand it your state at the current point in time, and it tells you what to do, how to turn the wheel, and whether to brake and accelerate. And you don't have a lot of insight into why it's making that decision, and so it's very hard to make guarantees about the safety of that system. The second big gap is the robustness of these machine learning-enabled controllers. Although they have some robustness to so-called in-distribution events, where if they've seen something before, they can be relatively good at responding to it. They have very poorly understood robustness properties for out-of-distribution events. If they haven't seen a disturbance or a situation before, it's very hard to react to it, and very hard to know ahead of time that we'll react appropriately. Control theory has some tools for answering these questions about safety guarantees and robustness, and the one that I'm going to talk about today is this idea of a certificate. So what I mean by a certificate is it's some easily checkable proof of a property of your dynamical system and controller. The example that I like to start with is this simple example of dropping a marble into this wiggly sort of bowl shape. Here, the property that we'd like to prove is that prove that no matter what happens, starting from some initial condition, the marble will never enter this red region, which is our unsafe region. What this proof might look like in the simple context is you can write down the total energy of the marble, gravitational plus kinetic, and you can say that the starting energy of this marble is not enough to reach this unsafe region because the unsafe region is at a high energy. And that counts as an easily checkable proof because I can write down the energy, I can hand it to someone else, and they can check my work and say, yeah, that checks out, this system is going to be safe. Now, I like to start with the energy example because it gives some nice intuition about what we mean by a certificate. But when we think about more complicated control tasks, we need to come up with a more generalized formulation for a certificate. For example, if we have this satellite rendezvous situation where we want the blue satellite to approach the target from a specific docking cone, we want to prove that the satellite will reach its target without entering this red region. And here we can't just write down the energy, but we can do something similar. We can use a concept from control theory called the Lyapunov barrier function. You might recognize this term from the title of the paper. You can think of this as a sort of generalized energy function. It has a minimum at the goal, or a local minimum near the goal. It has a level set that separates the safe from the unsafe regions, and it's decreasing along trajectory, so it's dissipating. And you can combine all of those things to say that whatever value this generalized energy starts at, it will always decrease along trajectories. And if all of your safe states are at low Lyapunov energy, and all of your unsafe states are at high energy, you know that you're never going to reach an unsafe state if you start somewhere safe. Mathematically, we have these 4 conditions here. It's not super important to understand exactly what's going on in these equations, but I want to throw them up here because they will be relevant later down the road when we talk about creating these certificates. These essentially map almost 1-to-1, in one case 2-to-1, onto these conditions. So it has a local minimum at the goal, that's the first line. The second and third are that you need to separate the safe and unsafe states, and the third condition is just saying that this is dissipating along trajectories. Once you have a certificate like this, you can use it for control in a relatively straightforward way, and Jeremy alluded to this in his Q&A earlier, which is that the certificate will give you not just one direction where the certificate is dissipating, where the energy is decreasing, but it can give you a range of directions that all cause this decrease. And if you have some sort of nominal controller, that might be unsafe. You don't need to have any guarantees on this nominal controller. All you need to do is project it into this range of permissible controls, and that will ensure that your system will stay safe and remain stable. This is a long and storied idea in control theory. It has good performance, and it has very low computational cost, and it does provide some of this transparency and safety guarantees that we're looking for. This is a pretty standard idea in control theory. You can find it in almost any controls textbook. But right after that, in the same textbook, you will see a line that says, it's almost impossible to find these functions by hand. Writing down this generalized energy to satisfy all of these conditions, that's very difficult for you to just come up with a polynomial that satisfies all of these conditions. And so that makes this very difficult to use. In the last 2 to 3 years, there's been a really exciting new trend in control theory research, which is saying that we don't know what these functions should look like exactly, but we do know how they should behave. We do know what the outputs of these functions should look like. And combining that with powerful function approximation tools such as neural networks, we can actually learn what these certificates should be, or learn an approximate certificate. And when we look at this class of tools for certificate learning, these fill in some of the important gaps when we look at other learning for control methods. They provide transparency and safety guarantees, because if you have this question, how well will this controller work, you can answer that by just looking at your certificate. They still leave a gap in terms of robustness. This is a relatively new field, and no one has looked at what do we need to do to make these certificates robust to some sort of uncertain disturbance. If we have wind, if we don't know the mass of our vehicle, how can we make sure that these certificates are still valid? And that's where this work is coming in. We're going to be extending this idea of certificate learning to account for this this issue of robustness. And this brings us to our key idea for this paper, which is that we can make learned controllers safer and more generalizable using this idea of a robust safety certificate. And there are 2 subproblems hiding in this. The first is that how do we make a certificate robust? And the second is how do we find a robust certificate? If you remember that the standard issue with Lyapunov functions certificates in general is that they're very difficult to find. If we're adding requirements that we also want them to be robust, that makes them only more difficult to find. And we'll talk about the tools that we use in a couple of slides. Okay, so for the rest of this talk, I'm going to be pulling together kind of 2 main ideas. One from control theory, where we're going to talk about what makes a robust certificate, and then another set of ideas from machine learning, which is how can we use neural networks to learn approximate robust certificates. We'll be combining those and showing that we can get some pretty cool results by the end of the talk. So first, how can we take this idea of a certificate and make it robust? The way that we can do this is we can think about quantifying our uncertainty through a range of extreme scenarios. So an example of that would be if you have uncertainty in the mass of your vehicle, you can imagine the low mass extreme and the high mass extreme. If you're thinking about wind, you can think about what happens if the wind is blowing hard from the right or hard from the left. So we can think about these extreme cases. If we look at what the range of permissible control inputs that our certificate gives us in each of these extreme cases of uncertainty, we can combine those by taking the intersection to get a robust permissible control set. And we can do a little bit of extra math by exploiting the structure of our dynamical equations to prove that as long as we stay inside this intersection, we will in fact be safe and stable no matter what values the uncertainty takes, as long as it's within these extreme scenarios. The issue here is that if you just take a standard certificate and try to take this intersection, you're not guaranteed that this intersection will be non-empty. You might run into the case where these two cones are pointing in different directions, and we want to avoid that. So that brings us to the next question of how can we learn a certificate that makes sure that we have a non-empty intersection here, that makes sure that they're useful when it comes to robust control. The way that we do this is calling back to the 4 conditions that I had on the earlier slides. These are modified slightly to include robustness in this last decrease condition. And again, it's not critical to go into what each of these equations is saying, but I just want to show the mapping. Just like before, we had this direct mapping from these intuitions about energy onto these conditions. Now we have a direct mapping from each of these conditions here into a loss function. So our loss function is going to contain one term for each of these conditions, and the loss term is going to be positive whenever the condition is violated, and 0 when the condition is satisfied. And so, for instance, we have this term that's dealing with saying that our certificate has to be decreasing along trajectories. We can map that directly into a loss term where we sample a bunch of points. We see, is it possible to find one control input that makes sure that this certificate decreases? If that is possible, the loss term is 0, and we try to minimize the loss so that the output of our neural network Lyapunov function ends up satisfying all of these conditions. So next I'm going to talk about what this buys us in terms of results. And I'm going to use this example of a self-driving car because I think it's informative. Here, the task is to track some trajectory, but the issue is that we don't know the trajectory ahead of time when we're designing this controller. We know that there's a range of maneuvers that we want this car to be able to do, say turning left, going straight, maybe going around some traffic cones, but we don't know ahead of time exactly what that trajectory is going to look like. So this is where the idea of robustness comes in. We do know that no matter what this trajectory does, it's going to be in between 2 extremes, and those extremes are turning hard to the left and turning hard to the right. And any other behavior that you can imagine for this car is going to be somewhere in between those 2 extremes. And so we train our certificate only on these 2 hard left and hard right examples. So these 2 circular driving plots are the only training examples that this system sees. And then we go and test how well it generalizes to a trajectory that is never before seen, this S-curve, where there are some similarities. You can see that there's some of this turning left, turning right behavior, but it's never seen this trajectory before training. And it still achieves really good performance. It achieves a good safety rate, and it tracks the trajectory pretty well. And what's more, we can go and look at the certificate that it generates, and we can sample at a large number of discrete points, and we can see, is this satisfying all of our certificate properties? If it does, that increases our confidence that this controller is going to be safe, stable, and generalizable. We also perform a number of different experiments. We have a whole range of our examples in the paper, and I'm happy to go into them in the backup slides. But we compare in particular with a robust model predictive control method, and we compare on these metrics of safety rate and the time it needed to evaluate the controller online. So on this left plot, higher is better. We want a better safety rate. And our approach achieves as good or better than robust model predictive control in all of our examples. And second, when it comes to control period, you want a lower control period to reduce the computational burden of running this controller. And our controller is much better than robust model predictive control. We're talking about 10, 15 milliseconds as opposed to 250 milliseconds. So in summary, we're making 3 main contributions in this paper. The first is theoretical. We're talking about how can we take this existing body of knowledge on certificates and extend that to the robust case. The second is practical, where we provide a machine learning framework for learning those certificates. And the third is that we show through a range of experimental results in simulation that our approach outperforms existing robust control methods. There are some drawbacks that we're working on addressing. The first is that we have a lack of hardware implementation in this paper. That's something that we're working on with a collaborator at another institution, and we've also done some hardware demonstrations in follow-up papers. Another main critique is that when we're talking about verifying these certificates, we're currently only doing that probabilistically. We check whether the certificates are valid at a large number of points. If it is, that increases our confidence that it's valid everywhere else. There are some tools that exist for exhaustively verifying the outputs of neural networks, but we just haven't explored that direction yet. right on time. That's my talk. Happy to take any questions.
So, sorry, are the certificates the Lyapunov function, or?
Yes.
Okay.
So there are a couple of different things that could be certificates. Here it's a Lyapunov barrier function.
Okay. So I'm just curious, what are the other examples of certificates, I guess?
So they're all kind of related to the property that you're trying to prove. If you only care about stability, then a standard Lyapunov function is a certificate for that. If you only care about avoiding an unsafe set, then you need a barrier certificate. Here we care about both of those, so we combine them into a Lyapunov barrier. Another common one is called a contraption metric. That's if you want to care about tracking performance. If you have a trajectory tracking controller, there are contraption metric certificates for that.
Okay. And then with the RL, it's just learning some the polynomial representation of that or whatever, basically.
So RL is typically not learning any form of certificate. It's just learning an input-output. Like you give it your current state, and it gives you the control action that it thinks you should take at that state.
What's like, for the robustness, you were saying that both of them aren't robust to like out of distribution things. What's like an example of that, I guess? And why are they not robust to those situations?
Yeah, so there are a couple of reasons that depend on the exact implementation of reinforcement learning that you're using. But the general intuition is that the way that these algorithms work is that you give them a bunch of examples, and it tests out some policy on that example, and then it uses the information it gets from that trial to improve its policy. So it's really, in some ways, it's doing a regression on you give it a bunch of examples, and it figures out how to do well on those examples. And that means that you just don't have any guarantees about how well it'll do if you go outside of the sample that you've regressed on.
How do you choose where to sample the points in order to get the certificate?
So we sample uniformly, but with a couple of caveats. So I can give an example where we have like a safe and an unsafe region. So here on the satellite, we have like this safe donut, and we have the unsafe center and the unsafe outside. We sample uniformly to start, and then we resample to make sure that we have at least 20% in the safe region, 20% in the unsafe region, and 20% in this border region. So that's just a heuristic that we found is helpful.
Is there any insight on how this will scale for a higher dimensional system?
Yeah, so I think the highest dimensional system that we deal with here is 9 dimensions, I believe. Yeah, so we go up to 9 dimensions. I know some of my lab mates are working on 16 dimensions. There are, when we're talking about scaling to multi-agent systems, one of my lab mates has done work where you can have decentralized certificates, so you can actually factor a multi-agent system into just the dimension of each agent and find a certificate for each agent, and then combine them to get system-level guarantees.
Great. Can you shed some light on the architecture of the neural networks?
Good question. So the architecture is fairly simple. We use a fully connected network. We have some standard choices. I think usually we start off with 2 layers of 32 units each, which is relatively small when you're talking about perception, relatively standard for control problems. And then we take the last layer of this fully connected network, and we take the 2 norm of it, or 2 norm squared. And that's just a trick to make sure that the output is always positive, because we know that this function is always positive.
Also, just a single layer.
2 hidden layers.
Sorry, 2 hidden layers. And I guess, was it difficult to prevent overfitting and stuff like that, since like these are just 32 overfits? Like, what was the amount of data you, so that how did you prevent overfitting if you had a problem?
Yeah, so we didn't really see an issue with overfitting, and I think that's because there is like some nice underlying smoothness in these functions. They're kind of behaving a little bit like energy, and energy doesn't have these like really antagonistic cases where it's very spiky, at least in our kind of control examples. In terms of training, commonly we use between 10,000 to 100,000 training points, and we do a like training validation split on those. That was more for debugging because we don't really have a good metric of accuracy. but that did just help us kind of debug and fine tune. We didn't see any issues with too much overfitting. Andrew, you had a question?
Yeah, maybe it's a little philosophical, but like, what are the, like, how do you know the limitations to your certificate? And just going back to like your very first simple problem with like dropping the marble in there, like how do you know that you're like missing like wind, for instance, that would like blow it out of the way, and like just some outside factor that you just don't know about?
Yeah, so the question about like unknown unknowns is a good one. I don't have a good answer for you in this work, but one of the main contributions that we're making is allowing people to handle the known unknowns. So before, in the case of the marble example, if you had wind, you would have just been kind of stuck in terms of coming up with a certificate. And here we have this formulation of a robust certificate that says, as long as you know that's there, you don't have to know the exact value, you just need to know like what the distribution of the wind is, and that will allow you to be safe. We don't have a good answer for if you just don't know what something is. You could model that as in your dynamics equations, like you have this differential equation. One way to model an unknown unknown is to just add a big additive term at the end where you say there's like some error that we're just not sure about, as little structure as possible imposed on that error. That will reduce your performance because you'll have to be more conservative.
Hi, Charles. Interesting talk. I'm just curious and want to make sure, is the work learning the control directly, or is it learning the Lyapunov function?
So we learn the Lyapunov function, and then we derive a controller from that using a quadratic program.
I see. Then the network, you have to take the derivative through the network, right?
Mm-hmm. Yeah, and we do that just by hand.
Okay.
We do a second forward pass that computes the derivative.
Yeah, I think there's a way to just get it directly from, like, from the neural network architecture. I think there's just some coding to get on.
Yeah, we did experiment with some autodiff stuff to get the derivative of the network. It was much faster to just write the derivative by hand in terms of multiplying weight matrices and stuff.
And I guess a follow-up. So you mentioned that you're sampling states that are kind of known to the designer, that those are the extreme scenarios. How do you expect the same sampling strategy to generalize to more complex systems, right? Maybe it's not so intuitive without the extreme scenarios.
Yeah, so the extreme scenarios are really about how we're quantifying the uncertainty in the system. Formally, we're assuming that these uncertain values come from some convex set, and we're assuming that you know the corner points of that convex set. Or more specifically, a convex hull of these scenarios, and we're assuming that you know those scenarios. So I guess that's an assumption in our problem statement, is that you need to know the shape of your uncertainty set.
So, very quick question. I know we're going to move on to feedback. You sort of said there are two extremes, and you're making an assumption that everything is in between. So that's just, you're assuming a convex uncertainty set?
So we assume a convex uncertainty set, and then we have a couple more technical assumptions that we assume that the dynamics are control affine, but moreover that they're parameter affine. So for any fixed state in control, the dynamics need to be affine in parameters. This allows it, we found that this is relatively general. It allows us to handle additive uncertainty, multiplicative uncertainty, mass, some frictions. We formulate our trajectory tracking problem so that the parameters of the trajectory enter affinely into the dynamics. We found that it ends up being relatively general. And then the way that shows up in proofs, if you're interested in like the proof sketch, is that this condition on the Lyapunov function, this is affine in the dynamics because inside this derivative is like gradient of v times dynamics. So we have this nice affine structure all the way that preserves